Okay, so again, before we start everything, I just want to show you guys the problems. Here we have Green's theorem, then we have some curl and divergence, more curl and divergence, tangent planes, that type of stuff we got going on here, surface integrals, surface area integrals, and then we go into actual just flux integrals, right? And then we go and we use some some Stokes theorem, and later on we end off all the way with divergence theorem. So we cover 11 problems in about an hour 30. So it's a little bit fast, but everything is explained in. I recommend what you do is you try to do all these problems before you watch the solution, and if you get them wrong, then watch what I did, or look at the slides that I will provide in this description, and you can compare your mistakes, or you may not have any mistakes. Good on you. Okay, time to fucking use some Green's theorem. Alright, so we're going to use Green's theorem to do this, and we could already think that, look, it's a circle, so it's going to go around. Probably should use Green's theorem, right? And let's assume positive orientation, so going clockwise. Alright, maybe I'll draw out the picture for you guys. So we have two circles, one with a radius 3, one with a radius 2. So that's the difference. Radius 2, 1, and this whole thing is 3. Okay. Alright, that's how circles work. And it's going around in a positive orientation. So our path would be like this, right? Okay. Nonetheless, let's compute this using the fact that Green's theorem goes F dot, I'll write it this way. We go P dx plus Q dy. Using Green's theorem, then we say double integral Qx minus Py dA. So that's the general idea of Green's theorem. Let's start by finding Qx and Py. Okay, Qx, derivative of Q with respect to x. As we can see, we're going to take this part. Oh, we're going to take this part, my bad. And we're going to take its derivative with respect to x. There's nothing here that has x. This is the only one with x, so it's 3x squared. Py, taking this with respect to y, it's going to be minus 3y squared. Okay. So now if we put this into a integral, double integral, it's going to be 3x squared minus, right? Minus, so plus 3y squared. Yay. And as you can see, it looks like we can factor out the 3, and then we're going to have x squared plus y squared. Now notice I didn't write what we're integrating over. We're integrating over some domain D. We don't know what that domain D is yet. We'll just write D. But we see that x squared and y squared means that we could probably use some sort of polar change of coordinates. So we'll write this as r squared r dr d theta. And then now we could look at our diagram and we can figure out what D is. So maybe we say that D, not maybe, we will say that D is from r, can be described with r and theta, where r is the radius. So minimum radius was 2, and then maximum radius was 3. And then theta, it goes around in a circle, so it's 0 theta to 2 pi. Okay. So all of that means we can write our double integral 2 pi, 0, and 3 to 2, 3 r squared r dr. Now r squared r, I'm going to write that as r cubed dr d theta. And as we can see, this is going to be 3 times 2 theta, not 3 times 2 pi, times the integral of 3 to 2 r cubed dr, which is the same thing as 6 pi r4 divided by 4, 3 to 2. And I'm going to factor out the 4, so I'm going to write this as 3 pi over 2. And 3 to the power 4, 3 to the power 4, 3 to the power 2 is 9, 9 times 9 is 81, so 81 minus, and 2 to the power 4 is 16. Okay, and then what's 81 minus 16? That may be the hardest part. 81 minus 16, well, 80 minus 16 is 54. No, 80 minus 16 is 64. So 64 plus 1 is 65. So we have 65 times 3 pi over 2. And 65 times 3, that's 180 plus 15, 195 over 2 times pi. So that is our answer. All that right there. Okay, Green's theorem again. Okay, let's write out the general form of Green's theorem. Okay, right, it goes f dot dr is equal to double integral of what? Curl of f dotted with the k hat dA. So that's a way to say Green's theorem, and in this case, it's what we can use. We can use Green's theorem. This may be a little bit unnecessary to write this, but this is just a reminder of what it is. I'll start by actually drawing and describing what this is. So it's a particle moving along the x-axis. So it starts at the origin, goes to 1 to 0, so goes to this point. With an arrow, so it's going down here, and then it goes up, then along the line segment to 0, 1. So then 0, 1's here, and back to the origin. So it's a triangle. That's what it is. It was just a really complicated way of saying this thing. Travels in a triangle. In a counterclockwise orientation. So it is a positive orientation. Okay. So all that's useful, but let's maybe make it actually usable, right? So our vector field F, we could generally describe it as P and Q. And then if we describe it that way, well, we see that P is equal to what? X squared plus XY. And then we see that Q is equal to XY squared. And since this is the 2D curl, so curl F is equal to cross F. But since this is, I'll say but 2D, we already kind of know how to predict this formula because it's been given in the textbook. It's going to be Qx minus Py. So we're going to take these guys and do that, and that's just the same thing as I have right here. Okay. So specifically for our case, we see that P, we're going to take Q, so Q is this one, and we're going to take its derivative with respect to x, which is just going to be y squared. And then we're going to minus P with respect to y, so this is P right here, taking that derivative with respect to y, which is going to be x. So this is our integrand. This is what we're going to integrate. So double integral d y squared minus x dA. Now, how do we describe d? That's the question. Well, we can describe d as some triangle, right? And we know that it's bounded from 0 to 1. So if I should maybe label this for you, 1, 1. So if that's true, then we know that x and y, well, x, you definitely know it's from 0 to 1. So 0, 1. How about y, though? You don't really, y is kind of different. It's kind of like it has a slope to it. So it's kind of a changing thing. It's kind of a weird thing to describe. Oh, it's not that weird because there's the equation for a slope, right? So we know it starts at, well, this line, we'll just describe this line real quick. This line is y equals negative x plus b. Right, okay. So we got to figure out, so y is equal to 1, just pick any point. Y is equal to 1, then x is 0 plus b. So b is equal to 1. And yeah, you could have read that. I just did the algebra this way just in case you aren't familiar with just reading it off. So we describe that line as y equals negative x plus 1. And we could check it for this point. So if x was 1, yeah, y is 0. Okay, that makes sense. So we could describe y being from what? Well, it goes from negative x plus 1 to 0. Okay. Starts here. It goes down to here. Okay. So specifically, our integral will be from what? 1 to 0. And then negative x plus 1 to 0. Y squared minus x dy dx. So let's actually do this integration. We'll start with the first integral. negative x plus 1, 0, y squared minus x dy. That's going to become y cubed over y minus xy negative x plus 1 to 0. We're going to, all we got to do is just insert this into here. Why is there a y? This should be 3. And it's going to be negative x plus 1 cubed divided by 3 minus x negative x plus 1. Okay, so this is going to be our next integrand. So now we're going to integrate all of that from 1 to 0. Negative x plus 1 cubed divided by 3 minus x negative x plus 1 and dx. Okay, and you're like, oh, I don't want to actually expand that. Yes, don't expand that. Please don't expand that. Do a substitution. So mu is equal to, gotta take off my headphones. Mu is equal to negative x plus 1. D mu is equal to negative dx. But notice we have x here. So we could kind of describe that by using this relationship. So if we write x is equal to 1 minus mu, and we insert that back in. And since we're changing our coordinates, we got to change our bounds. So we went from x, and now we're going mu. X was from 1 to 0. Mu will be what? So if we insert 1 into here, it'll be 0. If we insert 0 into here, it'll be 1. So it's the opposite. So our identical integral will be from 0 to 1. Mu cubed divided by 3 minus, now there's a minus x here, so I'll write this as 1 minus u times mu d mu. It's a negative d mu actually, right? Yeah, negative d mu. Okay. So that's our new integral. And since there's a negative d mu here, and our bounds are kind of in a weird position, if we flip our bounds, we can get rid of that negative d mu and write it as a regular d mu. So 1 to 0. And in the same time, we're going to write mu cubed divided by 3. And we're going to multiply this into here. So if we multiply it in, it'll be minus 1 minus, wait, let me just write it like this, damn it. Mu, God, this mu is looking ugly. Mu minus mu squared d mu. Okay, now we can integrate this nicely. So if we integrate this, this will be what? Mu to the 4th divided by 4. Let me make that look like actual 4 minus mu squared divided by 2 minus plus mu cubed divided by 3, 1 to 0. Let's insert 1 into all this. So we get 1/4 minus 1/2 plus 1/3. 1/4 plus 1/3 is 7/12 minus 6/12 because of 1/2, which is equal to 1/12. That's our answer, all of that. Okay, so for curl and divergence, these are the more conceptual parts of this calculus series. And for conceptual parts on it, it's good to do problems that just have geometry in them and to see the conceptual geometry, right? Okay, well, I'm going to write out a few facts for you. Well, divergence of f is equal to gradient dot f, right? And then curl of f is equal to the gradient cross f. So what does the gradient mean? The gradient is the derivative in all directions, right? Dx, dy, and dz. It's being applied to f, where f is equal to p, q. And in this case, instead of r, it's 0, right? Because we don't have any force in the z direction coming at us or going away from us, right? Literally says that in the problem. So if we apply these facts and we think about it, looking at number 9, is there any, you asked the question, is there change in x? No. Okay, so gradient cross gradient dot f is just equal to what? It would be dx dy dz vector dotted with only 0, q, and instead of r, it's 0. So it's just what? It's just q dy dq, which is qy. And is the derivative of q in the y direction, is this increasing? Is it increasing as we go up? So it looks like it's a big vector, then it becomes a smaller vector. So qy is, okay, qy is less than 0. Qy is decreasing. Qy is decreasing. Okay, and if qy is decreasing, then what? Well, then it says that the, damn it, I can't write divergence. Then divergence of f for number 9 is negative. Okay. What else? Well, the curl. Okay, so the curl, let's see if it says the same story. 0 and 0. So really, if we're to do this real quick, like I said, you can really just read these problems off, but I'm gonna do the calculus for you so you can see it before I do it with other problems. So it'd be what? Dx dy dz 0 0 q, and then its vector would be what? What would its vector be? So dy 0 0 dz q. So the only one would be negative dz q, right? And everything else would be 0 0. So that's our vector. Our vector is purely just in the I direction, and it's negative. So curl of f for number 9 is what? It's negative q with respect to z. And what does that mean? Okay. Is there any change in the z direction? Is there even a z component? Well, no, there isn't. And so negative q with respect to z is 0. So curl f is equal to 0. Okay. That's it. So I'll write the facts down right on number 9. I'll write them in red. So div is less than 0 and curl of f is equal to 0. That's all you need to know for number 9. Let's do the same thing for number 10 and 11. Okay, so let's start this the same way as we did last time, looking at number 10. So number 10 does show that there is what? There's change in x and there's change in y. So that means that what? Well, is the change in x and change in y the positive? Okay, so it's going in the positive direction, correct, but is it getting bigger? So it looks like this one, it's definitely getting bigger as it goes in the x direction. And it looks like it's getting bigger in the y direction. So this already tells us that div of f for number 10 is, it's what? It's positive. Okay, that's nice to know. That's all we needed right there. You could just visually see it. Same logic applies. Okay, how about the curl? So if I write same thing like I did last time, do dx, dy, dz, and then I write p and q and 0. Now it looks like this is like a diagonal vector, so assuming it's going in the same direction here and going in the same direction here, thus its resultant is really going like this, right? That's a diagonal vector, right? So p and q, I'm just gonna say blah blah blah, whatever this is, I don't really care, but I know that what's it called? Dx blank is going to be the resemblance of dy blank, whatever that is, right? Well, what does that mean? Well, it means that, remember 2D curl? 2D curl, it says what? Curl of f is equal to q with respect to x minus p with respect to y. So this would be q up here, and then this would be p. And what is this from? This is Green's theorem right here. This is Green's theorem. We've seen this in the Green's theorem integrand. So if q and x is equal, if q with respect to x and p with respect to y is equal to each other, then if they're in this thing, so this thing minus this thing is 0, so then equals 0. So curl of f equals 0. Okay. There we go. So div is greater than 0, div is positive, and curl of f is equal to 0. Okay. Yeah, and this last one will be the hardest one. Okay. So off the bat that we can see that there is no change in y. So we'll just scratch that out. There is a change in x, right? Now this change in x is kind of hard to describe. We see that there's one going here and there's one going here. But what else do we see? We also see that the change in x increases if what? If it's up. If it's higher in the graph. So in other words, let's just start by writing out what f we think it is. Well, we say that f is purely just going to be p, because there's no q component, there's no z component, so it's just p. Okay. So then if we do dot cross f, it is just equal to dp dx. Okay, and now this is the part where we ask ourselves a question. Okay. Is there a positive or negative change in x with respect to that single vector at that single height? Okay, so what I mean by that, look at this. Okay, so look at this row right here. It looks like all those vectors are the same. They're all going in the same direction and they're all the same length. Same here, same here, same here, same here. But all these vectors are not the same. If you go in this column, they're not all the same. But all we want to ask is p changing in x. Right? This vector is going in has the same length in the x direction as this vector. This vector has the same length in the x direction as this vector, and they're both in the same direction. So dp dx is equal to 0. Okay. Thus, div f is equal to 0. Okay. Now, curl of f. So, curl f, right? In 2D, again, same thing here. It's q x minus py k hat. Okay. Well, there's obviously, what, py? Qx doesn't even exist, right? So, just it's negative py k hat. That's it. Like, because we know that p is something that exists, and then if we take p's derivative with respect to y, then we get p negative py in the k hat. So that's our answer. So curl, our answers, I'll write them in red. Div f is equal to 0. Curl f is equal to, I'm going to write, I just want the direction. Right, so negative py in k hat. Or you could say it's py in negative k hat. Okay, that's the answer. Okay, so for this problem, what we want to do is we want to find the curl of everything in here. Okay, so let's start by just defining what that stuff actually means. So we want to find the kernel divergence. So divergence of f, right, is equal to the gradient times f as a dot product. And then curl is nearly the same thing, except it's going to be a vector product, because it's going to be gradient cross f. And I should actually say operator del. Operator del. That's what this is. Okay. So let's start by defining our general derivative here for what arctangent. So I'm just going to say dx of tan inverse, which is arctangent. What that is it's ddx of x, so whatever is in that spot x here, you put it right here, you take that's derivative, and then 1 plus x squared. So that's the formula. We're going to use this formula a lot. I just wanted to define that because we do a lot of derivatives here. Okay. We'll start with divergence since it's the easiest. So this dotted with f, in our case, is going to be what? It's going to be d. I'll write it this way. So all of this stuff, then we're going to take its derivative with respect to x, then with respect to y, and with respect to z. So it's going to be d dx tan inverse xy d dy tan inverse of yz and d dz of what? Of tan inverse cx. Okay. So what does that stuff actually do? What does it actually mean? What does it actually come out to? So derivative of tan inverse, where this is our inside, so it's like a little bit of a chain here, right? A little bit of the chain. So up top, we'll have something up top. So if we take this with respect to x, it'll look something like this, but instead of d dx at the top, it'll be d dx of xy, and d dx of xy will just be y. So this will be y over 1 plus x squared. And since this next one is with respect to y, and this last one is with respect to x, notice that since this one's with respect to x, we had a 1 plus x squared. So if this one's with respect to y, it'll be 1 plus y squared for the denominator. And then since it's with respect to y again, the top part will be d dy of yz. So d dy of yz is what? It's just z. So this will become z plus 1 plus y squared. And then like the pattern just continues. So this next one, it's going to be x and then 1 plus z squared. Okay. So that's our answer. That's our divergence right there. All of that. Actually, instead of writing it as a vector, I should probably take out the vector notation here. It's no longer a vector. And a dot product creates a scalar product. Sorry, I'm just so used to writing those brackets. The answer itself is correct. Just gotta do a little tweak of notation here. So it'll be plus, 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 plus. Okay, now that's a submittable answer. Sorry about that. It's important to know the difference between when something's a vector and when something's not, and to indicate if it is or not. Okay. For the second part, we're going to take the curl. So curl is going to be equal to the, okay, right? It'll be our del cross f, and we should write this as a determinant, where it's dx, dy, dz, and f. I'm going to call it p, q, and r just for the simplicity here. And I know that that turns into some vector. Oh no, don't want to do that. Damn it. I know that that turns into some vector that looks of the form like this, right? So it would be y with respect to r, so r with respect to y, minus q with respect to z. And then it's going to be r with respect to x, minus p with respect to z. And then the last part, I know it's the Green's theorem part for 2D, right? So it'd be something like this. It'd be q with respect to x minus p with respect to y. Like I said, you've seen this a lot by Green's theorem. So now let's actually just label what p, q, and r is. Maybe I should have made that clear. So this would be p, and this would be q, and this would be r. believe I've been using that notation before, so it should have not been that confusing. But if it was, I'm sorry. Okay. And by the way, this is a column vector, so this is a vector here. Right, you could put an arrow on top to indicate it's a vector, but usually you don't need to because everyone sees this as a vector usually. Most textbooks. Okay, nonetheless, r with respect to y. So r with respect to y. Okay, looks like there's not a single y term in here, so it's 0. Q with respect to z. Okay, there is a y term in here. No, there is a z term in here. So it would be something like this. Minus, because there's a minus here. But q with respect to z. So it's d dx of arctangent. I'll write it out. I'll go d dz of tan inverse yz. I won't skip steps on you guys, don't worry. Okay, next one. It's r with respect to x. So d dx of tan inverse zx. Then we're going to minus. And it's p with respect to z. Okay, right, real quick. R with respect to x. Yes, there is the x part. P with respect to z. There is no z component for this, so it'll just be 0. Okay. Now we're going to take q with respect to x. Okay, there is no x component here in this q, so it's just going to be 0. And the reason why I know that's 0 is just because if there is no x in this and we're taking its derivative with respect to x, then everything is just a constant, and the derivative of a constant is 0, right? Okay, and then we're taking p with respect to y, so there is a thing in here that we actually do. D dy of tan inverse xy. Okay, now we can take these derivatives and you'll know what I'm talking about here. So d dz of tan inverse y. Okay, it's going to be something like this, right? So it'd be y plus 1 plus z squared. What's the next one? Okay, instead of writing as a column vector, I'm going to write it as a bracket vector. So I'm just going to make it, instead of being vertical, horizontal. So it'd be negative 1 times z, no, times y, top. And then 1 plus z squared, comma. The next one's going to be z 1 plus x squared. There is a negative here. Next one is going to be x and 1 plus y squared. Yeah, there's a negative there again. So that's your curl vector right there. So notice there's everything's negative and everything has two variables in it. It's kind of equal opposite, right? That's the idea. Now I'm really sorry about this real quick. I don't want to give anybody the wrong idea, but the idea was there. I just obviously made a small little mistake. And it's an important mistake, so I want to show you guys the mistake and show you guys how to fix it real quick. So know how that, remember how I said that this is x and there's an x here, right? You take its derivative and then, well, there's also x here. So whatever x was, it could, in this case, this sounds funny, right? X was equal to x plus y. And maybe for the sake of this, I will change the notation real quick. I'll write it like this. I'll write it as d du tan inverse of u, d du, u, and u squared. And then now this would all make sense. And again, I'm terribly sorry about this. It's going to be 1 plus xy squared, then 1 plus yz squared, and 1 plus zx squared. So like I said, remember, these derivative rules, they're actually pretty important. And it shows you that it's very easy to mess up on them. But it's good to be honest when you mess up and admit your mistakes. That's what I'm doing. So again, everything is really correct. You just need to put the yz here in this case. And then you need to put the zx here in this case. and then put the xy here in this case. Okay, there we go. Now this is a good answer, and you can submit this. You can put this on your paper if you wanted. Okay, this next question requires a little bit of the use of the theorem. Not a little bit, it requires a lot of the use of the theorem. We say that f is conservative, right? We say that f is conservative if the curl of f is equal to 0. So that's the theorem that we use to tell if the field is conservative. Okay. And what we can do here is we can just take that curl. Let's just find the curl already. Okay. So I'm going to use this. Like, I'm just going to jump straight to this because this is useful. You should probably remember this. This is really nice right here. This is always true for 3D curl. Okay. So we'll write it ry minus qz negative rx minus pz, then qx minus py. And let's just fill in those gaps, right? Again, this is the formula for curl. Like, this is it right here. This is the formula. Okay. R with respect to y. So this is P, Q, and R. I'll label it again, P, Q, and R. All right, so R with respect to y. We're going to take this with respect to y. It's going to be 6xy z. 6xy z squared. Okay, everything else is a constant except the y squared term. And the minus q with respect to z. So it's going to be 6xy squared. 6xy z squared. So it's the same thing. And then let's see if negative. So rx. R with respect to x. We're just going to get rid of the x, just erase it. That's all you're going to do. 3y squared z squared minus and p with respect to z. So it's going to become 3y squared z squared. Oh my god, look at it. Is it going to be 0? Will it be 0? That's the question. If it's 0, then it's conservative. Okay, and then q. Let me make my q with respect to x a little bit more noticeable. That was q with respect to x. Q with respect to x. Okay, again, you just erase the x right there. 2 yz cubed. Then let's see. Okay. P with respect to y is going to be 2yz cubed. Okay, so everything cancels. It's equal to 0. And the field is conservative. I don't know if I spell conservative correct. It doesn't matter. Often I believe in spelling things wrong. Okay, next one. Okay, since it's conservative, we got a little bit more work to do. We got to find f such that little f and its gradient is equal to big F. Okay, so if you guys don't remember, we can go like this: F, F, and F. And it's kind of like the opposite now. So it's like, remember I took P, Q, and R. So I could write P, Q, and R. And remember I was taking derivatives of these? Well, now I'm going to be taking integrals of these. I'm going to be taking this one with respect to dx, with respect to dy, and dz. So this is like, yeah, it's just kind of like the reverse thing now, right? So instead of taking derivatives with respect to different differentials, now you're just straight up lining it up. So P will always go with dx, then you integrate it to find F. Q will always go with dy. R will always go with dz, right? That's just an easy way to remember it. Okay, so P is right here. So I'll just write it down: y squared z cubed dx, and then what's the next one? 2xy z cubed dy. And what's the other one? 3xy squared z squared dz. So let's just compute these real quick. This one will just be xy squared z cubed plus some c. Next one will be will be xy squared z cubed plus some c. And let me guess, is the next one xy squared z cubed plus c? It is. Yeah, it is. Okay, so that was pretty nice that it worked out. So f of x comma y comma z is equal to xy squared z cubed plus c. And then if we take that gradient, like that's our answer, by the way. This is all we have to give them. There you go. But if you don't believe in this answer, what you can do is you can check it. So we're going to take del f. So we're going to take all of this with respect to its certain variables. And then yes, you'd literally get this back. Like you'd literally just get that back. But if you take this again, just prove it to yourself. It'd be y squared z cubed. Next one would be 2xy squared z cubed. The next one would be 3xy squared z squared. And look at that. It's the same thing, same thing, same thing, same thing, same thing, and same thing. Okay, so it is true. It does work. That's all you needed to know. It works. Okay, so let's do some tangent planes. Okay, so we want to find the tangent plane at that point. Okay, well, we know that the formula for the tangent plane, we know that the formula for a plane, and I'll write this in green. So it's the normal vector. Damn it. You guys don't want to see that. You guys don't want to see me editing a video. It's a normal vector dotted with point, the position vector, and it's equal to 0. And then you ask, what is the normal vector? Well, the normal vector, it's equal to RU cross RV. Okay. Well, that's all you need to know. Okay, so first let's actually define what R is in this case. Well, R is XY Z. If you want to write it with using just U and V, they very nicely can do that. So it's U plus V, 3U squared, and U minus V. Okay, so then if you take R with respect to U, what do you get? So it'll be 1, and it'll be 6U, and it'll be 1. And you take R with respect to V, what do you get? You get 1, you get 0, and you get negative 1. Okay, so then if we take the cross product of this, so we'll write the cross product here, in this determinant form, 1, 6U, 1, 1, 0, negative 1. Okay, let's write it as a column vector because it's easier this way. So 6U times negative 1 is negative 6U. 1 times 0 is 0, so let's write minus 0 here. 1 times negative 1 is negative 1. 1 times 1 is 1. And then we got 1 times 0, which is 0, and 6U times 1. We'll clean it up a little bit. We'll see that's negative 6U, and it's going to be 2 and negative 6U. Okay. So then, if we think about this vector, okay, well, look at, so we could see that the x part is negative 6U. And then we see that the y part is 2. And the z part is 6U. So what can we do to find u? So if we set this equal to this, and this equal to this, and this equal to this, it will help us find what u, v, and that stuff is. But that's what we usually do. It's kind of nice that we have these points here. So we could just put that in directly. So let's write this little box right here. Okay, so we see that x is equal to 2, y is equal to 3, oh no, and z is equal to 0. Okay, well then we also see that x is equal to u plus v. Okay, well what does that mean? It means that u, actually let's use the y, equation. Y is equal to 3u squared, so then u has to be equal to either negative 1 or 1. Okay, well that's nice. Well, x is equal to u plus v, and x is equal to 2. So then now we can think about what is V. Okay. But maybe we can actually just do a systems of equations that might make this even easier than doing all this algebra. So we say Z is also equal to U minus V, but then Z is equal to 0. So let's add these. We see that we get 2U is equal to 2. So U is definitely equal to 1. So then we can go back up to the top and scratch out this negative 1. Okay. Now the reason why we do all that, you'll see in a second, but we need to know what U is equal to put into these. And then you could also see that we need to know what V is, okay? So if we know what U is, we could probably find out what V is pretty simply just by using this equation right here, or we could use this equation. I think we should use this one, it might be better. So U minus V is equal to 0, so U is equal to V. And that means that V is also equal to 1. So if we're just to check this real quick, so look, 1 minus 1 is 0. 1 plus 1 is 2. Right? So then we could see that our vector here, our normal vector, its components, it's going to be -6, -6, and 2. Again, all of this is important because you need to find these finite values that relate this normal vector to our position vector here. Okay, but I didn't really give you a position vector yet, right? Well, you don't really need to worry about that much because we kind of know that PO is some point that is this point. But then P is just some arbitrary other point. And since it's some random other point, we can just call it X. It's X minus this point, 2, and then the trend carries on. So 3, Y minus 3, and then Z minus 0 is just Z. Okay, so that's our position vector. So now, when we take the cross product of them, not the cross product, when we take the dot product, my bad. So I write out these vectors, so -6, 2, and -6, dotted with this right here, which is X minus 2, Y minus 3, and Z. Okay, well, what do we see? Okay, well, we see that this is going to be -6x plus 12. This is going to be 2y minus 6. And this is going to be -6z. And of course, we got to add these guys up. So we're going to add them up. Okay. And when we add them up, we're going to see that's going to be -6x minus 6z plus 2y and then plus 6. And again, all this is equal to 0, remember, because we have this formula. So this is your answer right here, but maybe we'll make it look a little bit nicer. So if we divide everything by 2, if we divide everything by -2, we would get 2x plus 2z plus y. We wouldn't get 2, we would get 3. If we divide everything by 2, this would be 3x. -2, this would be 3z. And then this part would be minus y. And then plus 6 divided by -3 is minus 2. Okay. Plus 6 divided by 2 is minus 3. For some reason I can't divide by 2 tonight. Okay, then you can make this look a little bit nicer. 3y. Wait, 1 second. 3y, 3z minus y is equal to 3. That's usually how you write it. And this is the answer you would submit. There you go. By the way, before I start the next problem, I just want to say that there was a shortcut. So since this is x equals uv, yeah, you could have, simply just done the dot product and then insert the stuff in later. You still get the same answer. I just do it this way because sometimes they don't give you this formula explicitly, right? So sometimes you need to solve for this type of stuff, and this is usually the way you would solve for this type of stuff. And nonetheless, let's move on to the next problem. So I'm going to go up here now. Okay. So we want to find the area of the surface. Ooh, that's hard. And we have a plane. Okay, and so we just have a plane in the first octant. So if we draw the first octant, we know that z, y, and x all have to be greater than 0 for it to actually stay in the first octant, right? And since it's some plane, draw some slash like that. if that makes any sense. Right? Because I don't know what the plane actually looks like, but just something like that. It's a plane in the first octant. Okay, and we need the formula for this, so I'm going to get the formula. Okay, so I searched up the formula real quick because I can't remember everything. Well, the formula for surface area for this would be the double integral over the surface, right? And specifically, it's going to be square root of 1 plus z with respect to x squared, and then plus z with respect to y squared, and then dA, of course, right? So this is the formula we're going to use. Just want to make sure I have it right. So I do have it right. Okay. So how do we describe S? Well, first off, why don't we just try to find these derivatives? Maybe that's even easier. So we want z as a function of x and y. So we can write it as z is equal to 6. Then we're going to minus the 3x and minus the 2y, put them on their sides. Okay, so now when we find z with respect to x, what is that going to equal? It's going to be negative 3. That's it. And then we find z with respect to y. What is that going to equal? It's going to equal to negative 2. Okay. I always like to find the actual integrand first before I find the bounds. Sometimes it helps with the way you think you're going to find the bounds later. So we get 1 plus negative 3 squared plus negative 2 squared. Okay, as you guys can guess, it's going to be 9, and this is going to be 4. 9 plus 4 plus 1, that's 9 plus 5. 9 plus 5 is what? Well, that is a little bit of a tricky math. It's 14, right? 9 plus 5 is 14. Okay, so this is your integrand. It's just a finite value, which is pretty nice. Okay, so if you want to integrate across the surface, which is the plane, so we have these relationships. Why don't we use them? Okay, so if we use them, we know that 0, z, and 6 minus 3x minus 2y is a relationship, right? However, is it a really good relationship? Not really, right? We have a double integral, so this is not a relationship we would really want to use, so we'll cross it out. Not that it's wrong, but there's a better relationship we can use. Well, we let z equal to 0, and then if z is equal to 0, then we just have 0 equals 6 minus 3x minus 2y. And then if we solve for y, we can see that we get y is equal to 6 minus 3x divided by 2, right? Okay, and then you know that y, so now you can use that relationship. So 0 to y to 6 minus 3x over 2. Okay, and since that's true, then let's just ask a question. What is x? Okay, well, x will definitely be from 0 to x. Yeah, but what's the biggest value of x? So we can find the biggest value of x if z equals 0 and if y equals 0. So essentially 6, 0, wait, 1 second, let me make it look a little bit nicer. We'll go back to this equation, and we're going to insert 0 into 2y and into z. So it's just going to be 3, x equals 6. X is equal to 2 at its max. Okay, so then we can go back and write 2. So now we have this double integral, finite value 2 to 0, and we have 6 minus 3x. I gotta make more space. 2 to 0. 6 minus 3x over 2, 0. And then I'm going to pull out the square root 14 because it's just a constant. And then we got dy dx. So that's the surface area. But of course you guys want me to actually do this integral for you. So square root 14, 2 to 0. And then the first integral, it's actually just going to be 6 minus 3x over 2. Okay, and then we could do a little bit more with this, right? We can factor we don't need a factor or anything. We'll just leave it. So we'll go 2 to 0. And 6 over 2, we're going to break this up. So it's going to be 3. And then we're going to go minus 2 to 0. This may be a little bit overkill. 3x over 2. And don't forget your differentials. Okay. So this is what we have. And then we can write this as what? Square root 14. And this one will be 6. And then it's going to be minus 3x squared. 3x squared. And then divided by 4, evaluated from 2 to 0. And then that's going to be square root 14, 6. Okay, and then 2 squared. 2 squared is 4. 3 times 4 is 12. 12 divided by 4 is 3. 6 minus 3 is 3. Not 2. I wrote 2 earlier. So, it's 3. Square root 14. Yeah, earlier I made a minor mistake. I mean, just right here I made a mistake and I said 6 minus 3 is 2. A little embarrassing, but, you know, that's math, right? Okay, for this problem, again, we're going to use Stokes' theorem. But earlier I was jumping. I was like saying, okay, we'll use this one instead of this, right? Well, we're going to verify that you can do both, right? Because that's the theorem. Okay, so I don't know. We can start off with f.dr, right? Because that's where everything begun in our vector calculus journey anyway. So start off with this, right? Okay, probably should try to find r, right? So we have a cone. Okay, so we can write that we have a cone, and, well, what does this mean? So z is equal to plus or minus x squared plus y squared. But it's saying that the cone goes from 0 to 4. So if we drew the cone, x, y, and z, right? The cone goes from 0 to 4, meaning it's upwards. Right, this is our cone. But our orientation is downwards. Okay. Okay. So that's all nice, right? And then we could just think about the curve, right? We're integrating along this curve at the top. So we know that curve is like this, and then we can represent this curve like we can use theta and r. So it goes from 0 to 2 pi, and its radius is what? Its radius, okay, well, it says z is equal to 4. So we could assume that its top radius, its biggest radius is 4, right? Okay. So if all that's true, then we can say our curve goes from 0 to 2 pi, and our radius is equal to 4. And then we could say that x is equal to r cosine theta, and in our case it's 4 cosine theta. And similarly, then y is equal to what? 4 sine theta. And we could say that z is what? Well, z is this. And we're going to pick the positive version. And we're only going to pick the positive version because, you know, we don't want to have 2 cones, right? We don't have 2 cones facing each other. We just have 1 cone. And z says it's from 0 to 4. So yes, we're picking the positive version of this. Nonetheless, z is going to be r squared cosine theta, r squared sine theta, which cosine squared sine squared theta, that's 1, and then we just get r squared here. So it's just, this just turns into r squared, which is just r. So z is equal to r. Okay. So, yeah, that's our vector r. Okay, and okay, real quick. So this is our radius vector, right? This is our radius vector. And since I don't want to have two r's, I'm going to call these our radius vectors big R's, just for the sake of not being confusing. Right. Okay, and then r is our reparametrization, which would be r cosine theta, r sine theta, and r. And again, for us, it's just going to be 4 cosine theta, 4 sine theta. And r, z is equal to r, then z is equal to 4, right? Okay, well, if we take dr, we get what? We get negative 4 sine theta, 4 cosine theta, 0 d theta. Okay, so I also need to change what f is. So f is negative y, x, and 2. Negative y, x, and negative 2. So this would become, if we insert this reparameterization, it would become negative 4 sine theta, 4 cosine theta, and negative 2 is just negative 2. Okay, so if I take this, so if I go f dot dr, I'm going to get this dotted with this. So negative 4 sine theta times negative 4 sine theta is 16 sine squared theta. 4 cosine theta times 4 cosine theta is 16 cosine squared theta. And then 0 times negative 2 is just 0. So this is 16. Okay, so our integral is from 2 pi to 0, 16. And okay, since this is oriented downwards, our vector is oriented downwards, right? Like it's pointing out down. So if we grab, like if you stick your thumb where the z-axis is, right, and pointing it out downwards, you'd see that your fingers are rotating clockwise, right? They're rotating clockwise now. So I'm going to go back to our circle and go clockwise, clockwise, clockwise. What that means is that f, like this, is 16, right? But we need to multiply this by negative 1 because our orientation is going this way. Okay. And this would be what? Just d theta right here. So this is f dot dr. I mean, look at it. Like it's simplified all down to this. And we just get that this is negative 32 pi. Okay. So if all that's true, if all that's true, then when we use Stokes' theorem, if we use the double integral over a surface, we go curl of f dot ds, then this should be equal to 32, negative 32 pi, right? If we do everything correct, that we should get the same answer, right? Because that's how Stokes' theorem works. So let's do that. And I don't know why my tablet is messing up real quick. Let's use Stokes' theorem. Okay, so let's just start by taking the curl. So the curl of f. And I'm going to go back and use this. So it's going to be ry minus qz minus rx minus pz qx minus py. So I copied it all down. So it's over here now. And then this is p, q, and r. And I'll write it p, q, and r. So I'm going to insert that stuff into here now. Okay, r with respect to y, 0. Q with respect to z is 0. R with respect to x is 0. P with respect to z is 0. Okay, now Q with respect to x is 1. P with respect to y is negative 1. So we get, what do we, out of all this we get, what do we get? We just get 2, and it's like in the k hat, okay? Okay, so that's the curl, and what's the ds? The ds is n dA, and then n. What do we want to use n as? Well, n is going to be our vector for r cross r, right? R cross r from different, with respect to different derivatives. So ru cross rv. But first we need what r actually is. So if we go back and we use this, right, but we don't insert the 4 for r, and we just write r, and I'm going to write our radius as rho. Okay, rho. Actually, I'll keep it as how it was. Big R cosine theta. And then big R sine theta. And then Z. Well, Z was just big R. So then if I take, I'm going to scratch this out. I want R with respect to R cos R with respect to theta. Okay, that's what I want. And let me write this as little r. Okay, so if I do that, then when I get r with respect to r, what do I get? I get cosine theta, sine theta, and 1. I take r with respect to theta, I get negative r sine theta, r cosine theta, and 0. So I'm going to put these guys in a determinant to take their cross product. And that'll be cosine theta, sine theta, 1, negative r sine theta, r cosine theta, 0. And I'm going to get this vector. So it's going to be 0, and then this will be negative r cosine theta. This next one is going to be 0, and then 1 minus minus, so it'll be r sine theta. The next one's going to be this guy times this guy. Right? Real quick. Cosine theta. Yeah. Let me make that look like that. Yeah, then I gotta take this. It'll be r cosine squared theta minus, so it's going to be plus r sine squared theta. And look at that. Just negative r cosine theta. This is going to be negative r sine theta. And this will just be big R. Okay. So that's n. So the curl times this. I need to make more space. Okay. Now let me take the cross product of this guy with this. I mean the dot product. Not bad. So it's going to be 0, 0, 2 times negative r cosine theta, negative r sine theta, and big R. What you get is 2r. Okay, that's what you get. Okay, and for the next part, right, so this is your integrand. Okay, so if that's your integrand, now you can go back and you can use this formula. I think it should be, we know it should be equal to negative 32 pi. Okay, now since this is a negative orientation, since it's oriented downwards here, and since it's oriented downwards, it's going to be counterclockwise, right? Clockwise is our negative orientation. So we're going to have our integral negative 1, negative 1's on the outside, and then it's going to be from 2 pi to 0, and then from 4 to 0. And then this will be our integrand, so it's going to be 2 big R, then d big R, and then d theta. Okay, and then the first one, factor out the negative 2 here. 2 pi to 0. Okay, we do this first integral. So just r dr, and then we're going to plug in 4 to 0. So that's going to be r squared divided by 2. Okay, and then r becomes 4. So 4 squared divided by 2. That's 16 divided by 2. That's 8. So you have 8 d theta. And then this is essentially the same thing as saying negative 4 pi times 8, which is negative 32 pi. Okay, there we go. Same answer. Look at that. Okay, so now we're going to be using Divergence Theorem. I'll write out the theorem. So it's saying that if we have a triple integral integrated over some shape, right, then we take its divergence of f and we integrate over a volume, then it's equal to what? It's equal to the surface integral, right? Not the surface, it's equal to the flux integral, which is this. Okay, so if that's true, then we can use this stuff, and both of these results should result in over some surface s. And everything should be the same, right? Okay, so I'm going to do the first part. I'm going to do just the divergence part in blue. So I'm going to do everything in blue, and then we should get the same answer when I do all this stuff in black. Okay. So we're going to use this. Oh my god, that was really ugly. Div f dot dv. We don't really need to write the dot because they're both not vectors, but let's find the divergence of f. So div of f is equal to what? It's the gradient cross f. Gradient dotted with f. So basically we take the partial derivative with respect to x, then with respect to y, and with respect to z. So if we take it with respect to x here, it's going to be 3. We take it with respect to y here, it's going to be x. And if we take it with respect to z here, it's 2x. So we get 3 plus 3x. Okay, well, that's our integrand. That's really nice, isn't it? Nice little simple integrand. We can write it as 3, 1 plus x to make it even nicer. So then we put that in our integrand. 3, 1 plus x. We'll go we'll do what? Dx, dy, z. And they already give us the bounds here. Look, so from 0 to 1, and then this one will be from 0 to, they're all from 0 to 1. Thank God, that's really nice. Okay, so if we take this, right, it'll be 3, and then the first, I'm not going to do it that way. I like to do things a little bit easier. 1 plus x, we integrate that, that's going to be x plus x squared divided by 2, and then we're going to put in 1 to 0, so it's 1 plus 1/2, which is 3/2. Okay. And then when we integrate again with respect to what? With respect to y, we notice we have no y, so it's going to be 3/2. Then we integrate again with respect to z, notice we have no z, it's going to be 3/2. And you do 3/2. And then now we have our constant on the outside, so then we're going to say times 3. And we get 9 over 2. Okay. So again, I just did the first integral, found it, and then I see that this is purely a function of x. So then the dy integral, it's just 1 times this, and then the dz integral is just 1 times this, and then remember we had a constant on the outside here. Okay. So it's 9 over 2. Really nice, really simple, but maybe the next part won't be so simple. Okay, so I'll draw the box here. I already messed it up. Okay, this is our box, right? And yeah, this is a nice box. What can we say? Well, we gotta take its, this involves orientation, so we're gonna say it's pointing out, pointing out, pointing out, pointing out, you know, everything's like pointing out, right? Okay. Well, with that said, we need to find the integration for the surface. So, how many surfaces do we have for a cube? We have 6 surfaces. Right, there's the top, bottom, back, side, front, you know, there's all those surfaces that we gotta integrate. Okay, this next problem, right, it's gonna be a lot more conceptual. So I did this once and I'll try to explain it a little bit better. So we have surface 1, surface 2, S3, S4, S5, and S6. Okay, we have 6 surfaces for a cube. Now, we'll call this, so everything that's like positive, meaning, so this is positive, it's going up. S2 will be its negative counterpart, it's going down. And then we'll call this S3, it's positive, and then S4 will be its negative. And then S5 will be its positive, and S6 will be its negative. So the negative part will be the evens. Okay. So notice for S1, it's a plane, right? It's outline of this. Okay, so if it's outline of this, we can use y and x. And the same thing goes for this one. It's also y and x. But, now look at this force. So if we had the force field here, if we had the force field in here, and it's encasing this cube, right? Or it's going through this cube, whatever you want to say, right? However you say it. We have this force and we have this cube, and we're trying to know the divergence, the flux outwards. So if we're just on this plane, right? What does this mean? Okay, well it means that where can the force go through? It can only go up. So there's no 3x and there's no xy. Right? So if you had to draw the force vector, it's coming around, it's in the z. Z. So the normal vector is 0, 0, 1. And then in this case, the normal vector is what? 0, 0, negative 1. Because it's pointing down, right? It's pointing down. Okay. And then I'm going to draw one shape and one shape because it's still the same square. It's just, positioned differently, right? Where the normal vector is a little different. But we'll always have normal vector, normal vector, normal vector, and normal vector. And notice it's a unit vector here. The reason why I can write it as a unit vector here because I'm just concerned about the direction for now. Okay. So for surface 3, I believe I was talking about going like this, right? So, okay, that's just purely in the what plane? So this is the xy plane, this is the y-axis, this is the x-axis, so this is in the xz plane. So, x, z. And this other one would be in the what? And be in the y, z plane. Okay. Now we know for, like I said, for surface 3 and 4, right, this one, and this one, shooting out this way, and shooting out this way. So where's the shooting out? It's shooting out in the j direction only. So it's going to be 0, 1, 0. And likewise, this one will be shooting out in the negative j direction. And then, as you can see, the pattern continues. This one can only shoot out in the what? This one can only shoot out in the what direction? In the x direction. It's a negative 1. Okay, so hopefully this makes sense. This is where these normal vectors come in. And this is really useful for this equation. And by the way, this equation, it's not just this one, this is the most compact form. But I'll write it up here. Do not want to do that. This is also the same thing as what? Surface surface over S, F dot n hat ds, where ds is no longer a vector. Okay. And ds is purely the norm of n, right? dA. Okay. Nonetheless, let's keep going here. So, what does this mean? Okay, so like I said, for surface 1, this being surface 1, it's only shooting out in the z direction. So, if we look at this plane, right, and we had to think about where is this plane located. It's located at z is equal to 1. And then how about this one? It's located at z is equal to 0. And then how about this one, surface 3, right? This one is located where y is equal to 1. And the other one is where y is equal to 0. And then yes, the pattern continues. Okay. So this is just talking about the location of where that plane is. So this plane, again, you can describe where it is. You can describe the top of the box. Say it's at z equals 1. and the flow coming out of it is just strictly in the z direction. Okay. So if all that's true, then when we set up these integrals, s, and then what is f? Okay, like I said, f, there's nothing in this direction, right? There's nothing in this direction either. There's only something in this direction. So it's 2xz, then dotted with what? With 0, 0. My bad. So I'll write out the full vector, and then I'll show you why it's going to look like that. So if I write out the full vector, f is what? 3x, xy, and 2xz. And then when it's dotted with this vector, it's 0, 0, 1 ds. Okay, so look at that. So then as you can see, that's what I meant earlier. I was kind of skipping a step earlier. I didn't want to do it because it might be confusing. So 0 times this, 0. 0 times this is 0. So there's no force coming out in that direction. There's only force possibly in this j direction, and it's described with this f vector. Okay, and I'm just setting up these integrals for now. Okay, and I'm going to do it again. 3x, xy, 2xz. And as you'll notice, in this case, it's 0, 0, negative 1 ds. Okay, and you can see that there's a pattern here again. So the pattern is that you put these vectors and you put f here, and then you see that these will cancel and there will only be one remaining. Okay, so if all that's true, then you can go wrong, and we're just going to call this p, q, and r for shorthand, and then we'll write 0, 1, 0 ds. We'll do s, p, q, and r dot 0, negative 1, 0 ds. And then this one will be double integral s, p, q, and r dot 0, 1, 0, my bad, 1, 0, 0 ds. Next one, same thing. I don't know why I keep writing brackets at integral. S, P, Q, R, negative 1, 0, 0 ds. Okay, I'm going to shift all these guys up a little bit. Okay, there we go. Now it looks according. So this is our stuff. Now, again, I'm not going to integrate right here. I'm going to do it somewhere else. But I just wanted to show this concept. So we'll call this I1, I2, I3, I4, I5, I6. I1, I2, and as you guys know, the pattern continues. Okay. I1. Now, if we do I1 and we simplify the integrand, we just get the double integral, and it's going to be 2xz ds. Okay, and then what is ds? So ds is the norm of this vector, the norm of this vector, and the norm of this vector, it's just 1. Like, it's just 1. Like, you think about it, right? The norm of this vector, so you take 0 squared, 0 squared, and 1 squared, and you square root it all, it's just 1. So ds is 1, and then what is it? See, look at the plane it's on. It's a d, it's a y and x plane, so it's going to be dx dy. So our integral is going to be from 1 to 0, 1 to 0, 2xz dx dy. Okay, and you're like, but there's a z here. What do we do? This is why I wrote this earlier. Okay, there's a z here, so then you know z is equal to 1. So we can rewrite this integral, and since z is 1, then it's just going to be 1 to 0, 1 to 0. 2x dx dy. Okay, that's the integral. That's all it is. Now what does it become? It's going to become, well, it's going to be 1 times, and then x squared over 2 from 1 to 0, which is just going to be 1/2. So the flux going through this surface is 1/2. Okay, 1/2 whatever units that is. that's going through that surface. Okay, that's a simple answer. Now, I'm going to do I2 here. Okay, I2, it's going to be nearly the same thing. 1 to 0, 1 to 0. And notice that we have a negative right here. So when we do our dot product, what do we have? We'll have a negative 2xe here. And then, yes, again, we can jump to the dx dy part. But what do we have over here? If we look at the cube, right? If we look at the cube and then we're looking at the bottom floor, we can describe its location as z is equal to 0. So then if we put in z is equal to 0, we get 0. Okay. So as you can see, for y equals 0, for like, what integral is this? This 1, 2, 3, 4. For the fourth integral, for I4, for this integral, it's going to be 0. For the sixth integral, it's going to be 0. So 0 and 0. Okay? So I'll write and for I4 and I6. Okay, there's no flux going through this surface downwards. There's no flux going through this surface over here. And if you guys need another explanation for why that is, look at this force field. This is a positive force field, right? It's a positive force field. Okay. Nonetheless, we can continue. And I need more space, so I'm going to make more space. Okay, hopefully that's a little bit better. Hopefully I was able to make a little bit more space. Okay, now all I gotta do is do I3 and I5. And these integrals should be that bad. So this is I3, so it's going to be 1 times q. So we're only going to have this component here, right? So our integral is just going to be this component for integrand, so it's going to be xy. And it's going to be dz dx, right? dz dx. And then what do we know? Okay, and then we know that y, since it's a dz dx integral, we know that y is equal to 1. So we know our integrals from 1 to 0, 1 to 0. Y is equal to 1. So just x dz dx. Which means that, what is this? This is going to be x squared over 2. Right? And then we can write this one as 1/2. That's the answer. Okay, similar story for this one. So it's only going to be the p component. So right here, this is going to be our integrand, 3x. And where is this? This is in the y and z plane, so it's going to be dy dz. And it goes from 1 to 0, 1 to 0. And then we know that x is 1. So this is just going to be 3. Yeah, that's it. Look at that. Isn't that nice? Right? Okay, so total flux. It's the sum. Okay, so it's the sum of all I sub n. And what does that equal? So in this case, it's just equal to 3 plus 1/2 plus 1/2, right? Which is 4. Sorry, I hope you caught it real quick before I close it off. I mean, this whole thing's supposed to be equal, right? So I know I made a mistake. I almost forgot that about this little mistake, and I saw it last second. Look at that. There's a 1, and then there's a 2. I mean, I kind of just made that 2 disappear, right? So let me go in. And yeah, this makes me sad right here. That's a 2. So then this is 1. Everything else is correct. Don't worry. So what is this? This is 4 plus 1/2, and the 4 plus... So this would be 8 over 2. 8 over 2 plus 1 over 2 is 9 over 2. I hope you caught that before I did. Right? We should have the same answer, and that's how we know that Stokes Divergence Theorem, my bad, Divergence Theorem is true, right? So we know that the flux going through this box, we can either use divergence, which would have been a lot faster and easier, I mean, as you see. Or we could use these flux integrals and do them for every single surface, right? Okay, this will be the last problem that we do, and it's a divergence problem. So for divergence, we want to find the flux to the surface, given this force field. Okay, so what we can do, well, we can realize that the formula we're most likely going to use is E divergence F dot, not dot, just dV. Divergence of F is not a vector, it's a scalar. Let's start by finding the actual divergence. So div F is equal to the gradient cross, I keep saying cross, dotted with F. So it's the partial of this with respect to x, partial of this with respect to y, partial of this with respect to z. So if we take this with respect to x, we get y plus 2z. And then if we take this with respect to y, we get 2y. If we take this with respect to z, what do we get? We just get negative 2z. So as you can see, these will cancel, and then this will be added to this, which is just equal to 3y. Okay. So that's our integrand. Now we got to think about how we describe E. Okay, so looks like we have a cylinder. Right, we have some cylinder, and then it gets cut by this plane like that, right? And it also starts at the bottom, right? So this is our surface. This is what it looks like, and specifically this area over here, right? Like this is the main cylinder. Like that's the part of the cylinder that we want to find a flux to. Okay. So we could see that, well, x squared plus y squared, well, that's the cylinder, right? And we could represent that using polar if we just had to talk about the cylinder. But then we see that z is bounded. So if we just are talking about the base of the cylinder, which is a circle, and it has a radius 2, then we can use d to describe it, the domain, right? And we'll describe it using r and theta, and then r is from what? 0 to 2. Theta is from 0 to 2 pi. Okay, that's useful. But what about z? So we know z goes from 0 to z to y minus 2, right? And then why don't we write this using polar? Y minus 2 as r sine theta minus 2. So this will be our first integral, and this will be our second integral. Okay, so now when I write the integral, it's going to be 2 pi to 0 from 2 to 0. And then we're going to have this other integral in front of it all, which will be r sine theta minus 2 from 0. And then our integrand was this, 3y. But I'm going to write that, I'm going to put the 3 in front of everything, by the way, too. I'm going to write just as y, and then y. Okay, so then y is what? Y would be r sine theta. And then note that this first integral is a dz integral. So we can close it. But then we have a Jacobian after, since we're in this plane, the r theta plane. We go dr d theta. So this is your answer right here. I mean, you just got to compute this. So we'll do the first integral, which is this one, r sine theta minus 2 to 0, r sine theta dz. As you can see, that it's just going to become r sine theta times what? This minus this, which is just this. So r sine theta minus 2. And we'll write this out as r squared sine squared theta minus 2r sine theta. Right, so we're just distributing it out. Okay, so that's our next integrand. So our next integral will be the radius integral from 2 to 0. Now it's going to be this as our integrand, but we also have a Jacobian here, so we're going to times this by r when we put it over here. So it's going to become r cubed sine squared theta minus 2r squared sine theta dr. Okay, so when we integrate this, this will become r to the fourth divided by 4 sine squared theta minus 2r cubed divided by 3 sine theta. And then we're going to insert 2 and 0 on this. Okay. Now, 2 to the power 4 is 16. 16 divided by 4 is 4. So we have 4 sine squared theta. And then for this one, this is also 2 to the power 4, just because this is 2. So 2 times 2 cubed is 8. 8 times 2 is 16. 16 divided by 3, we call it 16 over 3 sine theta. Okay, so this is our last integrand. And this is going to be our integrand from 3 times 3 from 2 pi to 0. And we'll have 4 sine squared theta minus 16 over 3 sine theta d theta. Okay, and now what I'm going to do is I'm going to break it into parts here. So there is a sine squared here, and I'm just going to have it by itself. So sine squared theta, and then 3 times 4 in front of it, so there will be a 12 in front of it. And it's from 2 pi to 0. And you guys just got to trust me on this. I mean, I've done this integral a lot of times. I think I even have videos of me doing this integral on my channel. But by now, I think we've seen this integral so much that we know it's just the integral of just this is pi. So it's 12 pi here. Okay, next one we got. We have the integral from, so 3 times 3. I mean, 3 times 1/3 is 1. So we have negative 16, 2 pi to 0, sine theta, d theta. And if you guys don't believe me when I say this, that this is equal to 0, I'll draw it out. We have sine, which I believe looks like this, right? And this is from 0 to 2 pi. And the area over here is equal to the area over here. Thus, the area under the curve is equal to 0. So this is 0. Okay. So now we know that the flux is equal to what? The flux is just equal to 12 pi. So a little bit of, just intuitive and memorization at the end here. So I compute those integrals super fast, right? That's how you can do some of these integrals super fast, is you start seeing the trend in the trigonometry.